All right, let's talk about acceleration. So here's how you can use this video. While you're watching this, on the slides there's going to be green highlighted text. If you're using this to take notes, you should write that down. That's the important material. Also throughout this video there should be some blue text. These are questions for you to answer, like practice problems or questions for you to consider. Also throughout this video there's going to be a visual code that will show up on the screen, and there will also be a verbal code said by myself. It can happen in either order, so just pay attention. All right, let's get started. So let's talk about acceleration. Acceleration is the rate at which velocity changes. So there are three ways to accelerate: speed up, slow down, and turn. This might seem counterintuitive because you might have just thought accelerate is speed up. Well, yes, but in terms of physics, you are the rate at which velocity changes. Now, this is going to come into play later, but a net force must be applied in order for an object to accelerate. Now, acceleration is a vector quantity, which means it has both magnitude and direction. So we'll talk about the direction of acceleration a little bit later. Now, the unit is meters per second squared. So second squared isn't like an actual unit, but meters per second squared mean meters per second per second. It's rate of change of velocity over the time. So that means an acceleration of 2 meters per second squared means the velocity increases by 2 meters per second each second. That's what meters per second squared means. Now, the equation is the change in velocity over the change in time. So this is what the equation looks like. And you see here, this is a complicated equation up here. It's not really that complicated. It just has additional information. Those arrows over some of those variables means they're vector quantities. That triangle T, that's the Greek letter delta, that means change in time. That means it happens over a time interval. The math is the same, right? It's just addition, subtraction, multiplication, division, right? It's final velocity minus the initial velocity, that's your change in velocity, over the time interval. Now, I've also made this little equation triangle to help you to isolate some of the variables in this equation, and we'll use this later. So we can get practice calculating acceleration here. So what I'm going to do is I have four questions up here, and each one of these focuses on a different one of the variables. So let's just take a look at that first one, right? A cart speeds up from an initial velocity of 2 meters per second to a final velocity of 10 meters per second in 4 seconds. What is the acceleration of the cart? So I am looking for the acceleration. Now, I know the initial velocity is 2 meters per second. I know the final velocity is 10 meters per second. And I know the time is 4 seconds. So that's what I know. We'll go move this over here. Now, I can set up this equation. Now, the equation is already set up, right? So the acceleration here, I already have that written up here. And I can set this up. The final velocity is 10. The initial velocity is 2. And the time is 4 seconds. So you got to remember your order of operations. 10 minus 2 is 8. I'll put an equal sign there. And it's all over 4. And so that means my acceleration is 2 meters per second squared. Right. So that's one of those problems that you can do. Now, let me just go ahead and clear this and just put those equations that you might need, because this is going to help you isolate some of those variables here, right? So I've got this one up here. This was acceleration. This one is finding the initial velocity. Oh, sorry, I skipped over one. How long does this take? That one's time. And the last one is the final velocity, right? So that one's kind of tricky because I gave you a bunch of different information you don't really need for it. So that one's a little bit tricky. So I'm just going to go ahead and put these equations up there. And this is the same equation. I'm just rearranging it to isolate that variable, right? So the one with the acceleration equals the final velocity minus the initial velocity over the time. Great. That's to find the acceleration. Now, if I need to find the final velocity equals, well, that is going to be the acceleration times the time plus the initial velocity. And you got to remember your order of operations there. All right, and I put 0 just because that means that times 0, how fast is it going? Now to find the initial velocity, right, that is going to be negative acceleration times the time interval plus the final velocity. That one's the tricky one, right? Because if you cover it up, that top part has those two variables. And the last one, you cover up time, that's going to equal the final velocity minus the initial velocity, oops, all over the acceleration, right? So you can do any problem just using these equations here, right? And I'll leave that up there, right? Oops. All right. So any of those the problems. So I'll leave this up there. You can go ahead and pause this, and you can practice doing these problems. So now moving on. Now we need to talk about the direction of the acceleration, right? So you can have a negative acceleration, but that doesn't necessarily mean it's slowing down. The direction of the acceleration depends on how the object's velocity is changing. So you can speed up, that's the same. If you speed up, the acceleration is in the same direction as the velocity. If you're slowing down, the acceleration is the opposite direction of the velocity. If you're turning, the acceleration is pointing towards the center of the circle. That's called centripetal acceleration. And if you're traveling at a constant velocity or at rest, you have 0 acceleration, right? So positive and negative describe directions, not whether something is speeding up or slowing down. And the problems we did before, I had them going in a positive or a positive velocity. So yes, positive and negative acceleration did mean speeding up and slowing down. But if it's moving in the other direction, that's going to mean it really depends on the velocity. What direction is it moving? What is it doing? Is it speeding up or slowing down? So let's get practice just looking at this here, right? So these are called ticker tape diagrams. So these are diagrams showing a car dripping oil at a constant rate. The diagram shows the car's ending position. So for each diagram, answer these following questions. Is the car speeding up, slowing down, or at a constant velocity? What is the direction of the velocity? And what is the direction of the acceleration? So we need to look at this, and I'm just going to do a couple of them, right? I'm just going to do, let's just do this one, right? I'll do the bottom ones because they're moving in a positive direction, right? So that's going to be easy here, right? So I'll take a look at these three, right? So if you take a look and it's dripping, you should be able to tell whether it's speeding up, slowing down, or a constant velocity. This one right here, this one is slowing down. You can see the drips are slowing down. They're getting closer together. This one is speeding up. Now this one down here is traveling at a constant velocity. It's dripping oil at a constant rate. Those dots are the same distance apart. Now the direction of the velocity in all of these is positive. So now you need to put that part together that we just talked about and say, okay, well, what direction is the velocity? Well, they're all going in the positive. Now you need to ask, is it speeding up, slowing down, or turning? And saying, well, if it's speeding up, the acceleration is in the same direction. If it's slowing down, it's in the opposite direction. If it's at a constant velocity, there is no acceleration. So I'll let you pause this so you can practice these. And these are the 6 problems that'll help you with all the scenarios that you could imagine without turning. So now let's talk about that. Could you accelerate without changing speed? Now this is a little bit tricky here, right? So let's just take a look at the controls in a car. So you've got the steering wheel, you've got the gas pedal, you've got the brake pedal. So which controls change speed? Now speed is a vector quantity. It only has magnitude. So the gas pedal and the brake pedal, those change the speed. Which controls can change direction? Well, that's the steering wheel. Which controls can change velocity? Velocity, speed, plus direction. All 3 of them do. Which controls can cause acceleration? Remember the 3 ways to accelerate: speed up, slow down, and turn. Now this last one, is there a way for a car to accelerate but not change speed? If you're turning at a constant speed, you are accelerating. Right? Think about getting like on or off the off-ramp onto the highway. If you're traveling at like 30 miles per hour, you're get on that off-ramp and you're turning, you're going the same speed, but you are technically accelerating because you are turning, right? So that's just a little distinction between this vocabulary: speed, velocity, and acceleration. One note, like if we're talking about an object falling, right? Objects near Earth's surface experience a constant acceleration due to gravity. This acceleration does change based on where you are, but it's approximately negative 9.81 meters per second squared. Negative means down, right? It's accelerating down. All objects accelerate at the same rate in a vacuum. That means no air resistance. So if you take a look at this, a bowling ball and feathers are dropped in a vacuum, they're going to accelerate at negative 9.81 meters per second squared. And I also put this little clip over here of, this is one of the, I think, Apollo 15 astronauts. They're dropping a feather and a hammer on the moon. We notice they're accelerating at the same rate down because there's no atmosphere on the moon, right? It accelerates slower than Earth, but there's no atmosphere. So this is something to consider, like if you're doing problems, well, this is the acceleration of objects if they are falling down, or even going upwards, right? Because even going upwards, gravity is still pulling it down. So now let's get to the graphs here, right? So we're going to look at three different graphs. So the first one is a position versus time graph. So time is plotted on the x-axis and position is plotted on the y-axis. The slope of a position versus time graph represents velocity. If it's horizontal, it means at rest, zero velocity. If it's linear, it's a constant velocity. If it's nonlinear, that means there is acceleration. The steeper the line, the faster the object is moving. So here's a little graph that shows that. But I like this one down here, this little graphic here. And this one shows like this blue car, well, it's two cars, right? So notice the slope, right, of that line, the blue car, well, it's shallower than the red car. The red car is moving faster. Now, what this means is horizontal means straight left and right. That means you're at rest, right? Linear means constant velocity. Right, so you're traveling at a constant velocity. Now nonlinear, right, it means curved. That means acceleration. You're speeding up or slowing down, and that's what that final graphic down there shows. Now let's take this up to the velocity versus time graph. So let's just pretend we're graphing the slope of a position versus time graph here. So velocity versus time graph shows how velocity changes over time. So the slope of a velocity versus time graph represents acceleration now. At this time, I'll go ahead and give you that verbal code. The verbal code is 092. I say that again, it's 092. Now, horizontal, right, straight left and right means constant velocity, zero acceleration, right? Linear means it is constant acceleration. Now, nonlinear means you have changing acceleration, which is also called jerk. But we don't talk about that one too much. Steeper slope means a greater acceleration. And this one's more, this one like gets into like calculus here. The area under velocity versus time graph represents displacement. But let's take a look at these graphics here. So you can see here that blue car, just like we see in the oil drop, is traveling at a constant velocity, and the slope is horizontal, so there is no acceleration, right? Rise over run. Like if you don't have any rise, the slope is zero. Now that red car is accelerating. It's increasing its velocity. So you can see here the slope, it's a linear slope, and then it travels at a constant speed, so the slope is horizontal. There's no acceleration. Now, the last graph here is the velocity versus time. Okay, that one was twice. All right, we'll skip over that one. Now the last one is I think I just hit up backwards. All right, the last one is the acceleration versus time graph, right? So now the acceleration versus time graph, this puts this all together. So the slope of an acceleration versus time graph represents rate of change of acceleration or jerk. So I'm not like, this gets a little bit trickier here, right? Because a line on zero means constant velocity, zero acceleration. A horizontal line means constant acceleration. Linear means changing acceleration. Nonlinear means changing jerk, which is also called snap. And then it goes crackle and pop, right? So now we're getting into a little bit of calculus here to get our next set of equations here. But you can see here, these are not isolated here. These are like, if you have motion, you can graph position, velocity, and acceleration versus time. So I have three different scenarios here, right? With the top one, traveling at a constant velocity, right? So you can see the position, the velocity, and acceleration. Well, the position versus time is a linear curve, meaning the velocity versus time graph is a horizontal line, and then the acceleration is on zero. There's no acceleration. Now, if you look at the bottom two, they are, or the middle one, it's accelerating, right? So that means my position versus time graph is nonlinear. It's curved. The slope is always changing, so you can see that it's you can see that the slope is always changing, meaning the velocity is always changing. So the velocity versus time graph is linear, meaning the acceleration is changing. Or no, sorry, meaning the velocity is always changing, but it's a linear line, so that means the acceleration remains the same, and the acceleration is a horizontal line, meaning the acceleration is not changing. All right, and you can see the bottom one. Now we're getting into the negatives going left, so that one's a little bit trickier, right? So all of these go together, right? Like all of these go together. If you have some sort of a motion, you can graph the position versus time. So on these, right, I'm just going to do a couple of these really quickly, right? So for each of these motion graphs, make a ticker tape diagram. So just like we saw, or just like we've done before, right? So I'll go ahead and make this. So I'll do this first one for you, right? So it's slowing down to the right, sign of velocity is positive, sign of acceleration is negative, right? So imagine here, I'll draw a little car, right? It's moving to the right, here's positive, here's negative, so that means it's moving in this direction. So I'll draw the little car over here, right? So I'll just draw the wheels. Great. So this is what it's going to look like. So it's slowing down to the right, so that means that those dots are going to be getting closer and yeah, so here I'll draw those about the same, right? So it's going, the dots are going to be getting closer and closer and closer together, right? That's not the best one, but as it's going, it's slowing down. That's what it's going to look like, roughly, right? So I'll let you do the rest of those, right? Because it tells you what direction they're moving, the velocity, and that acceleration. So now let's get practice generating those motion graphs. So for all of these, draw the position versus time graph, draw the velocity versus time graph, draw the acceleration versus time graph. I'm going to go ahead and get this out here. I'm just going to do the, you know what, I'll do the, oh, you know what, I like this. I'll do this first one because it's going to have a negative acceleration here, right? So it's going to start here. Now, I know the velocity is going to be tricky because it does start positive and it's going to get slower and slower and it's going to be negative, right? So that's what it's going to look like, right? So the velocity versus time graph is going to look like that because it eventually comes to rest, right? It's starting positive and it's getting slower. Now, that means the slope of this line is the acceleration. I have a negative acceleration because it's moving in the positive direction, meaning the acceleration has to be in the opposite direction. Now, the position versus time graph is a little bit tricky. It's going to look like this, right? It's going to look like this because it is slowing down. It's a nonlinear curve, and you can see, like, if I lay a line tangent, well, it's positive there, and then it's zero up here, right? So I know it's going to be like that. So that gets a little bit tricky for that one. So I'll let you go ahead, just look at these. Practice making the position, velocity, and acceleration time graph for all these scenarios. So these are like the 6 scenarios that you can do for these kind of graphs. Then it gets complicated if they stop and then go the other direction and things like that. But these are like pretty simple scenarios. So now let's get to the kinematic equations. So the kinematic equations describe motion using the 4 conditions: time, position, velocity, and acceleration. So now we're putting them all together, and we get these equations from the graphs because of that, and that's like a little bit of calculus, right? So like the slope of a position versus time graph is the velocity. The slope of a velocity versus time graph is the acceleration. So that's how we get these equations. This puts all those together: time, position, velocity, and acceleration. They show how one condition affects the others. Not every now, here's the thing. Here's how you solve this, right? There's 5 variables up here. You only need 3 to calculate the other 2, right? So this sort of puts it all together when we're talking about calculating motion. So here's some practice problems. And you'll notice these are the exact same problems, just to save time. These are the exact same problems that we did for acceleration, but for all of these, now I'm asking you to find the displacement, right? So these are good example problems for that. So I'll let you pause this, and you can practice using these. So just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.